a telescope just found the frozen building blocks of life inside another galaxy. Water ice, carbon dioxide, the same chemistry that exists inside every living cell on Earth, locked inside clouds of dust 160,000 light-years away. We have always assumed life here was a special accident. Webb just found evidence that the universe disagrees. We will go inside a frozen molecular cloud, trace the exact chemicals that sparked life on Earth, and follow them across galaxies. If you enjoy the ride, subscribe so you never miss what we find next. Now, brace yourselves. We begin. A signal came through that stopped a room full of scientists. The James Webb Space Telescope had been staring at a dense cloud of gas and dust inside the large Magellanic Cloud, a small galaxy sitting right next to our own Milky Way. When the data came back, the team saw something layered inside the frozen dark. Molecules. Specific ones. The kind that, on Earth, are found inside every living thing. Webb did not find a planet. Webb did not find a signal from an intelligent civilization. What it found was quieter than that, and in many ways more important. Frozen inside clouds of interstellar dust, it detected water ice, carbon dioxide, carbonyl sulfide, methanol, and carbon monoxide. All together, all in the same place, all 160,000 light-years away, inside a galaxy that is a neighbor to ours. Scientists already knew these molecules existed in space. They had found traces of them before, scattered and faint. But finding them together, layered, concentrated, and chemically organized inside another galaxy, that was something different. That crossed a line. The detection happened because Webb carries instruments tuned to infrared light. Infrared is the kind of light you feel as heat. Regular telescopes cannot see it well because Earth's atmosphere blocks most of it, and older space telescopes lacked the sensitivity. Webb was built specifically to capture this kind of light, and these frozen molecules leave a very clear infrared fingerprint. Each one absorbs infrared at a slightly different frequency, like a unique musical note. Webb heard all of them at once, playing together from the same cloud. The cloud itself is called a dense molecular cloud. Picture a region of space so thick with gas and dust that starlight can barely pass through it. From the outside, it looks like a dark smear against the brightness behind it. On the inside, temperatures drop to around 400 degrees below 0 Fahrenheit. Almost nothing moves. Reactions that would take seconds in a lab take millions of years out there. And yet, chemistry still happens. Here is where it gets strange. That chemistry is organized. Scientists expected to find some simple molecules scattered randomly. What Webb showed instead was a structure. The molecules are arranged in layers around tiny dust grains, like an onion. Water ice on the outside. Carbon dioxide mixed in. More complex molecules buried deeper. This kind of layering means the chemistry built up over time, in stages, following a specific order. That order matters enormously, because the same kind of ordered chemistry is what drives biological processes on Earth. A team of researchers had been waiting years for this kind of detection. When Webb launched in late 2021, one of the stated goals was to study icy molecules in star-forming regions. This was the payoff. A single observation run produced a catalogue of molecules richer than anything previously recorded from outside our own galaxy. One of the lead scientists described the result as seeing, for the first time, the full ingredient list. Every item on that list had been found before, in different places, but finding them together, in the right ratios, inside another galaxy, pushed the idea of life's chemistry from a local curiosity into something that looks universal. And the molecules Webb found are not random, they are specific. Each one plays a known role in the chemistry that leads toward life. What those roles are, and why these particular molecules matter so deeply, is what makes the next part of this story so hard to set aside. Forget everything you picture when you hear the word ice. On Earth, ice is water. It forms at 32 degrees Fahrenheit, it melts in your hand, and it floats in your drink. Space ice is a completely different thing. Out in the cold dark between stars, ice is not a pure substance, it is a chemical mixture. A frozen soup of dozens of different molecules, all clinging together around a speck of dust, smaller than a grain of sand on a beach. These grains are everywhere. A dense molecular cloud like the one Webb studied contains trillions upon trillions of them, drifting in near-perfect silence at temperatures so low that molecules which would be gases on Earth turn solid instantly. When a molecule in the gas phase drifts close enough to one of these grains, the cold pulls it in. It sticks. Then another molecule arrives and sticks on top of it. Over millions of years, layers build up. The result is something scientists call an ice mantle. Think of each tiny dust grain as a seed, and the ice mantle as the shell that grows around it. That shell can contain water, carbon dioxide, carbon monoxide, methanol, ammonia, methane, and dozens of other compounds, all frozen in place, all pressed close together. At those temperatures, around 400 degrees below 0 Fahrenheit, the molecules cannot move freely. They are locked in position, suspended in chemical time. But here is the part that shifts the picture entirely. Locked does not mean inactive. Even at those extreme temperatures, a small amount of chemistry still happens. High-energy particles called cosmic rays punch through the cloud constantly, passing through the ice mantles and knocking molecules around at the atomic level. Ultraviolet light from distant stars trickles in and triggers slow reactions between the frozen compounds. Over millions of years, these reactions build new molecules inside the ice, ones that were never there when the grain first formed. Some of those new molecules are complex organic compounds. Scientists have produced these reactions in laboratory experiments, cooling mixtures of simple space molecules to near absolute zero and bombarding them with ultraviolet radiation. The results are consistent. Every time, new molecules form, and many of them are the same ones found inside meteorites and comets that have been studied here on Earth. Webb detected the chemical signature of these ice mantles from 160,000 light-years away. The infrared light passing through the cloud carried the fingerprints of each frozen layer, and Webb's instruments separated them with enough precision to identify individual molecules. Seeing these specific chemicals layered in this specific order is not a coincidence. It reflects a real physical process, one that operates the same way whether the cloud is inside our galaxy or sitting inside a neighbor galaxy across a gap of space that takes light 160,000 years to cross. That consistency is the signal. The universe runs the same chemistry everywhere it gets the chance. The dust grains carrying these ice mantles are incredibly small. A single one is roughly 1/10 the width of a human hair, yet each one is a tiny chemical reactor, slowly building complexity in the dark, waiting for the moment conditions change. What happens when that moment arrives? When heat finally reaches the frozen mantle, sets off a chain of events that scientists are still working to fully understand. That chain starts the moment a nearby star is born. And when it starts, everything accelerates. Pick any point in the night sky visible from the southern hemisphere, and on a clear night you can see it with your naked eye. The large Magellanic cloud hangs there like a detached piece of the Milky Way, a smudge of light that early navigators used to track their position at sea. For centuries, people looked at it and saw a cloud. What it actually is an entire galaxy, smaller than ours, irregular in shape, but packed with hundreds of millions of stars and enormous regions of gas and dust where new stars are forming right now. Its distance is what makes it scientifically extraordinary. 160,000 light-years sounds impossibly far. In the context of the universe, it is practically next door. The nearest large galaxy to our own, the Andromeda Galaxy, sits about 2.5 million light-years away. The Large Magellanic Cloud is more than 15 times closer than that. For astronomers studying molecules in space, that proximity is everything. At that distance, Webb's instruments can resolve individual regions inside the galaxy. Scientists can point the telescope at a specific molecular cloud, a specific star-forming zone, and get a clear, detailed signal from it. Do the same thing with a galaxy billions of light-years away, and the signal blurs into noise. The Large Magellanic Cloud sits close enough that the chemistry happening inside it is readable. The specific region Webb targeted is a dense molecular cloud sitting near an area of active star formation. This location is important. Molecular clouds near star-forming regions are in a particular phase of their life cycle, still cold enough to preserve frozen molecules, but close enough to young stars that the chemistry inside them is being slowly activated. Scientists describe this as a sweet spot, too close to a star, and the ice evaporates before it can be studied. Too far, and the signal is too faint to read. Webb caught this cloud at exactly the right moment. There is another reason this galaxy is valuable for this kind of research. Its chemical composition is different from the Milky Way. The Large Magellanic Cloud contains fewer heavy elements, things like iron, silicon, and sulfur, compared to our galaxy. Astronomers call this a low metallicity environment. Scientists had assumed that complex chemistry might be harder to achieve in low metallicity environments because some of the building blocks seem less abundant. Webb's detection overturned that assumption. The frozen molecules were there anyway, in rich variety, in a galaxy where the raw materials were supposed to be scarcer. That forces a revision. If the chemistry works in a low metallicity galaxy like this one, it very likely works across a much wider range of galactic environments than scientists previously modeled. The cloud Webb studied is surrounded by young, massive stars pouring out ultraviolet radiation. That radiation is slowly heating the outer edges of the cloud. The frozen molecules on those edges are starting to evaporate, entering the gas phase, and becoming available for the next stage of chemistry. Webb captured this process in mid-action. For researchers, this is as close to watching chemistry in real time as space science gets. The molecules Webb identified inside this cloud are the same ones scientists have been tracking in our own galaxy for decades. Seeing them reproduced, in the same combinations, in a different galaxy with different conditions, does something specific to the scientific argument. It suggests these molecules do not need our galaxy. They do not need our conditions. They show up anyway. What those molecules are, individually, and why each one made scientists pay close attention, is the next piece of the story. Each molecule Webb detected has a name, a structure, and a role in the story of life. The list reads like a supply manifest for building a living cell. Water ice, carbon dioxide, carbon monoxide, methanol, carbonyl sulfide, ammonia, each one frozen inside the ice mantles of dust grains, each one carrying a specific chemical function that scientists have studied for decades in the context of how life begins. Start with water ice. This one seems obvious, but its presence in a molecular cloud outside our galaxy matters more than it first appears. Water is not just a liquid life swims in. It is an active participant in chemistry. Water molecules bond to other compounds. They create environments where reactions can happen, and when they eventually melt or evaporate, they carry other molecules with them. Finding water ice layered around dust grains in another galaxy confirms that one of the most fundamental requirements for complex chemistry is widespread across the universe. Carbon dioxide comes next. On Earth, carbon dioxide is the gas you exhale. The gas plants absorb to grow. In frozen form, inside a molecular cloud, it acts as a chemical partner. Under ultraviolet radiation, frozen carbon dioxide reacts with other molecules in the ice mantle to produce more complex organic compounds. Scientists have run these reactions in labs and watched carbon dioxide contribute directly to the formation of molecules that appear in living organisms. Carbon monoxide is related but behaves differently. It freezes at a lower temperature than carbon dioxide, meaning it stays frozen even in the coldest, darkest cores of molecular clouds where almost nothing else survives. Its presence here tells scientists about the temperature history of this particular cloud. Carbon monoxide ice is a timestamp. Methanol is where things start to pull forward toward biology. Methanol is a simple alcohol, one carbon atom bonded to 3 hydrogen atoms and 1 oxygen atom. By itself, it has no biological function. But when methanol is irradiated inside an ice mantle, it produces a cascade of more complex molecules. Some of those molecules are amino acid precursors. Some are the kind of carbon chain structures found in cell membranes. Methanol is the starter compound. Finding it frozen and concentrated in another galaxy is finding the first page of a recipe. Then there is carbonyl sulfide. This one surprised people. Carbonyl sulfide is a molecule with sulfur at its center, bonded to both carbon and oxygen. On Earth, it appears in volcanic gases, in hot springs, and in certain metabolic processes in microorganisms. In early Earth chemistry models, carbonyl sulfide plays a direct role in helping amino acids link together into chains, which is the step that turns raw chemicals into proteins. Finding it frozen in an interstellar cloud 160,000 light-years away is finding evidence that this particular chemistry is not something Earth invented. The universe produced it first. Ammonia rounds out the major detections. Ammonia contains nitrogen, and nitrogen is essential for building amino acids and DNA. Its presence in the ice mantle means the cloud carries all 4 of the main elements that biological molecules are built from: carbon, hydrogen, oxygen, and nitrogen, with sulfur as a bonus. Together, these molecules form something scientists call a prebiotic inventory. Every item on the list has a documented role in the chain of reactions that, under the right conditions, leads toward the chemistry of life. Webb found all of them, in one cloud, in another galaxy. What happens to that inventory when a star is born nearby and floods the cloud with heat is where this story takes its first sharp turn. For most of human history, we studied the universe using only the light our eyes can see. That visible spectrum, the rainbow of colors from red to violet, carries enormous information, but it is a thin slice of everything the universe actually broadcasts. Below red light, invisible to human eyes, lies infrared radiation, and infrared is where frozen molecules speak. Every molecule absorbs and emits light at specific frequencies, like a fingerprint made of color. When infrared light passes through a cloud of frozen molecules, each compound absorbs a slightly different set of those frequencies. What arrives at a detector on the other side carries gaps, each gap the signature of a specific molecule. Webb reads those gaps and identifies what is in the cloud, even from 160,000 light-years away. Previous space telescopes had infrared capabilities, but they were limited. The Hubble Space Telescope was designed primarily for visible and ultraviolet light. Earlier infrared observatories existed, but their detectors were smaller, less sensitive, and struggled to resolve faint signals from distant regions. They could detect the brightest, most obvious molecular signatures in nearby clouds inside our own galaxy. Reaching into another galaxy and pulling out a layered chemical catalog was beyond them. Webb changed this completely. Its primary mirror stretches 21 feet across, roughly 3 times wider than Hubble's. That size alone collects vastly more light, but the instruments behind that mirror matter just as much. Webb carries a spectrograph called the near-infrared spectrograph and another called the mid-infrared instrument. Together, they cover a range of infrared frequencies wide enough to capture signatures from dozens of different molecules in a single observation. The team that made this discovery pointed Webb at a background star located behind the molecular cloud they wanted to study. That star acts as a flashlight. Its light passes through the cloud, picks up the molecular fingerprints of everything frozen inside, and arrives at Webb carrying all of those signatures embedded in it. Webb's spectrographs then spread that light out across its detectors, and scientists read the fingerprints one by one. This technique is called absorption spectroscopy. It has been used in astronomy for over a century, but Webb brought the sensitivity needed to apply it to a target in another galaxy. The signal from the background star was faint. The cloud it passed through was full of dust that scatters and blocks light. Webb's instruments were sensitive enough to pull the molecular fingerprints out of the noise anyway. The data came back as a spectrum, a graph showing which infrared frequencies were absorbed. Each dip in that graph corresponds to a molecule. The deeper the dip, the more of that molecule is present. When scientists looked at the spectrum from this molecular cloud, the dips were clear and unmistakable. Water ice, carbon dioxide, carbonyl, sulfide, methanol, all of them present, all of them layered, all of them from a galaxy next door. Webb is stationed about 1 million miles from Earth, sitting at a gravitational balance point where it can observe without Earth's heat interfering with its infrared detectors. It runs at a temperature colder than 260 degrees below 0 Fahrenheit. That extreme cold is necessary because infrared detectors pick up heat from their own surroundings. Webb has to be colder than what it is trying to see. The engineering required to build and maintain that instrument is extraordinary. But the science it enables is the point. And the science says the molecules of life are not rare. They are not hidden. They are sitting frozen in the dark in another galaxy, waiting to be warmed up. What triggers that warming and what it unleashes when it happens is where the story accelerates. Inside the large Magellanic Cloud, there is a region where space stops being empty. Dense molecular clouds are among the strangest environments in the universe. From the outside, they appear as dark patches, regions where the background stars seem to vanish. That darkness is real. The cloud is so thick with gas and dust that it blocks light almost completely. A cloud like this can stretch across dozens of light years and contain enough material to build thousands of stars. Inside it, the density is still far lower than anything we could create in a lab on Earth, but by space standards, it is packed. The cloud Webb targeted sits inside one of the most active star-forming regions in the large Magellanic Cloud. Surrounding it are massive young stars, some of them dozens of times heavier than our Sun, blazing with ultraviolet radiation and powerful stellar winds. These stars are recent. They formed from material in nearby clouds, and their birth changed the environment around them dramatically. Those massive stars are slowly destroying the cloud from the outside in. Their ultraviolet radiation strips electrons off atoms at the cloud's edges, creating a glowing boundary called a photodissociation region. Stellar winds push physical pressure into the cloud, compressing some regions while shredding others. The outer layers of the cloud are evaporating. Molecules that spent millions of years frozen solid are now entering the gas phase and dispersing into the surrounding space. But the inner core of the cloud is still intact. Deep inside, shielded by the surrounding layers of gas and dust, temperatures remain brutally cold. The frozen ice mantles on the dust grains survive there, still carrying their molecular inventory undisturbed. Webb's infrared observation reached through the cloud's edge and into those preserved inner regions. This two-zone structure is critical to the discovery. Scientists were looking at a molecular cloud in the process of being destroyed from the outside, while remaining chemically preserved on the inside. That timing made it possible to study the ice mantles before the heat reached them. A few million years from now, this cloud may be gone, dispersed into the surrounding galaxy. Webb caught it at the exact right moment in its life cycle. The environment around this cloud is also unusual in terms of radiation intensity. The nearby massive stars produce far more ultraviolet radiation than a typical stellar neighborhood would. Scientists had expected this intense radiation to break down complex molecules faster than they could form. The Webb data showed the opposite. The ice mantles were rich and complex, despite the harsh environment. The dust grains themselves act as shields, protecting the molecules frozen inside from the worst of the radiation. This finding matters beyond this one cloud. It means that even in harsh, radiation-flooded regions of space, the chemistry of life's ingredients can survive. The protection mechanism is simple. Freeze the molecules, coat them in more ice, and surround them with dust. The physics of the ice mantle turns a hostile environment into a chemical shelter. There is one more detail about this specific environment that adds weight to everything Webb found. The cloud sits in a galaxy with fewer heavy elements than our own. The dust grains available to carry ice mantles are less abundant there than in the Milky Way. Scientists modeled this environment and predicted that ice chemistry would be less developed because of it. The prediction was wrong. The chemistry was there anyway, equally complex, equally organized, equally loaded, with the same molecules found in our own galaxy's star-forming clouds. That failure of the model is, scientifically speaking, a very exciting result, and the implications of what survived inside that cloud reach far beyond one molecular cloud in one neighboring galaxy. Every molecule Webb detected inside that frozen cloud has a direct line to something inside a living cell. This is the part of the story that makes biochemists pause. Space chemistry and Earth biology are usually treated as separate fields with almost no overlap. One deals with the cold emptiness between stars, the other deals with warm, wet, complex systems inside living organisms. But the molecules Webb found sit exactly at the intersection of both. Take the carbon, hydrogen, oxygen, and nitrogen atoms present in that molecular cloud. Those four elements make up roughly 96% of the mass of every living thing on Earth. They form the backbone of amino acids, which are the building blocks of proteins. They form the rings of nucleotide bases, which are the building blocks of DNA and RNA. Life on Earth is almost entirely built from those four atoms in various arrangements. Webb found all four locked inside frozen molecules in a cloud in another galaxy. Methanol is a particularly sharp example. By itself, methanol is a simple compound with no direct biological role. But when methanol is trapped in an ice mantle and exposed to ultraviolet radiation over millions of years, it breaks apart and recombines into longer, more complex molecules. Laboratory simulations of this exact process have produced glycolaldehyde, which is the simplest sugar molecule. Sugars are the energy currency of living cells. They form the backbone of RNA. Producing a sugar from frozen methanol in a lab simulation, using only conditions that exist in space, is a result that biologists find difficult to dismiss. Carbonyl sulfide does something even more direct. In prebiotic chemistry experiments, the kind scientists run to understand how life first appeared on Earth, carbonyl sulfide drives the polymerization of amino acids. Polymerization is the process where individual amino acid molecules link together into chains, and those chains fold into proteins. Without that linking process, you can have all the amino acids in the universe and still never get a protein. Carbonyl sulfide catalyzes that critical step. Finding it frozen in an interstellar cloud is finding the chemical tool that could carry chemistry from simple molecules all the way to functional proteins. The layered structure of the ice mantles also matters here. The molecules are arranged in a specific order from the inside of the ice layer to the outside. Water ice dominates the outer layer. Carbon dioxide and carbon monoxide sit in mixed layers below it. More reactive molecules like methanol and carbonyl sulfide concentrate toward the inner layers where conditions were different when they formed. This is not random mixing. The layering reflects a sequence of chemical reactions that built complexity step by step, each molecule enabling the next reaction. That sequential, layered chemistry looks familiar to biologists. Biological systems also operate in layers and sequences. Reaction 1 produces the substrate for reaction 2. Reaction 2 produces the enzyme that drives reaction 3. Life is built on chemical chains, where each step enables the next. The ice mantles Webb observed are running a simpler version of the same logic. Scientists are careful to point out that finding these molecules does not confirm that life exists or existed in this galaxy. A list of ingredients is not a meal. Amino acid precursors are not amino acids. Amino acids are not proteins. Proteins are not cells. Each step between here and life is a genuine chemical challenge that requires specific conditions to cross. But the presence of this full ingredient list, in the right proportions, in the right combinations, in a galaxy 160,000 light-years away, means something fundamental. The universe is not randomly scattering a few simple atoms and leaving life to figure out the rest. It is producing the specific molecules life needs, organizing them into structured ice layers, and seeding entire galaxies with them. How those molecules survive long enough to reach a planet is the next piece of the puzzle. The molecules Webb found should not have survived. The region surrounding that molecular cloud is bathed in intense ultraviolet radiation from nearby massive stars. Ultraviolet light destroys complex molecules. It breaks chemical bonds, strips atoms from compounds, and reduces organized structures back into simple fragments. In the open gas phase of space, most of the molecules Webb detected would have broken apart long before they could accumulate into a detectable signal. The fact that they survived comes down to one mechanism: the ice mantle. When a molecule freezes onto a dust grain and becomes part of an ice layer, its vulnerability changes completely. The ice above it absorbs incoming radiation before it can reach the deeper layers. The water ice on the outer shell of the mantle acts as a physical barrier, taking the hit from ultraviolet photons so the molecules buried below it stay intact. Scientists call this self-shielding. The outer layer of ice sacrifices itself chemically while protecting the inner layers. The ice itself also changes how radiation interacts with the molecules. In the gas phase, a single ultraviolet photon hits a molecule directly and can shatter it. Inside the ice, a photon that reaches a molecule may not have enough energy left to break its bonds. The surrounding ice matrix absorbs and distributes the energy, spreading it across many molecules instead of focusing it on one. The ice acts like a shock absorber for chemical damage. This is confirmed experimentally. Laboratory teams have taken mixtures of simple molecules identical to what space ice contains, frozen them to temperatures matching molecular clouds, bombarded them with ultraviolet radiation for extended periods, and then analyzed what remains. The results are consistent. The outer layers break down, but the inner layers survive. Survival rates for complex molecules inside ice mantles are dramatically higher than in the open gas phase. Cosmic rays add another layer to this story. These are high-energy particles, mostly protons, that travel across the galaxy at nearly the speed of light. Cosmic rays penetrate ice mantles deeply, passing through the outer layers and reaching the interior. When a cosmic ray strikes a molecule inside the ice, it deposits energy. That energy can break bonds, but it can also form new ones. Some of the most complex molecules found in ice mantles appear to form specifically through cosmic ray bombardment of simpler compounds. The radiation that seems destructive is also a driver of complexity. This dual role of radiation, destroyer and builder, depending on whether a molecule is exposed or protected, explains how the molecular inventory Webb observed could have built up over millions of years inside a hostile environment. The cloud was being irradiated the entire time. The ice was both accumulating damage on its surface and building chemical complexity in its interior. The dust grains themselves contribute to survival. The size of a typical interstellar dust grain, around 1/10 of a micrometer, is just large enough to cast a radiation shadow. Molecules sitting on the protected side of a grain during certain periods of the cloud's history would have experienced dramatically lower radiation doses. Over millions of years, even small differences in radiation exposure add up to large differences in molecular complexity. What all of this means is that the universe has engineered, through simple physics, a system for building and protecting complex chemistry in the coldest, most hostile environments imaginable. The cold is the factory, the ice is the vault. And when that vault finally opens, when heat from a newborn star reaches the frozen mantle, what spills out into space carries everything that accumulated inside. What comes next in that process is stranger than it sounds at first. The grain is 1/10,000,000th of a meter wide. You could fit 10,000 of them across the width of a single human hair. And it is building the chemistry of life. Interstellar dust grains are the hidden infrastructure of the universe's chemistry. They are tiny, they are everywhere, and without them, most of the complex molecules scientists find in molecular clouds would not exist. The grain is not a passive particle drifting through space. It is a surface, and surfaces are where chemistry happens. In the gas phase of space, two molecules can collide and react, but collisions are rare. Space is extraordinarily empty, even inside a dense molecular cloud. Two atoms floating freely might drift for thousands of years without encountering each other. But when both atoms land on the surface of a dust grain, the rules change. The grain holds them in place. They cannot drift away. They sit close together, and eventually, one of them migrates across the grain's surface and runs into the other. They react. A new molecule forms. This process is called grain surface chemistry, and it drives the production of some of the most important molecules in space. Molecular hydrogen, the most abundant molecule in the universe, forms almost entirely through this process. Two hydrogen atoms cannot easily combine in the gas phase, but on a grain surface they form hydrogen molecules reliably. Scientists confirmed this decades ago, and it transformed the way they understood interstellar chemistry. Water forms the same way. An oxygen atom lands on a grain. A hydrogen atom arrives and bonds with it. Another hydrogen atom arrives and completes the water molecule. That water molecule stays frozen on the grain's surface, becoming the foundation for the ice mantle that builds up around it. Every layer of ice that grows on top adds more surface area for more reactions. The grain's surface also acts as a catalyst. Certain reactions between molecules require energy to get started, and that energy barrier is too high to cross in the gas phase. On the grain surface, the geometry of the surface itself can lower that energy barrier, allowing reactions to proceed that would otherwise stall. This is the same principle behind the catalysts used in industrial chemistry on Earth, except the catalyst here is a speck of cosmic dust formed in the atmosphere of a dying star. Temperature matters enormously for how the grain operates as a reactor. At around 400 degrees below 0 Fahrenheit, molecules that land on the grain freeze immediately and stay put. Slightly warmer, around 300 degrees below 0, some molecules gain enough energy to move across the surface before freezing. That mobility is productive, allowing more molecules to find each other and react. Too warm, and molecules evaporate before they can react or accumulate. The coldest molecular clouds maintain exactly the right temperature range for maximum chemical production. Webb's detection of layered ice mantles is direct evidence that this grain surface chemistry has been running for millions of years in the large Magellanic Cloud. The layers are a record. Water ice first, then carbon dioxide mixed in as carbon-bearing molecules arrived. Then more complex compounds built from the ones below them. The grain did not organize this. Physics did. Gravity brought the molecules down to the grain. Cold kept them there. Radiation and time did the rest. There are trillions of these grains inside a single molecular cloud, each one running the same slow chemistry, each one building the same kinds of molecular inventories. Across millions of years, a cloud accumulates an enormous reservoir of complex, frozen chemistry, distributed across every grain inside it. When something disturbs that reservoir, the results propagate across an entire star-forming region. That disturbance has a name. It has been happening next door for millions of years. And what it releases into space is the part of this story that connects a frozen cloud in another galaxy directly to the ground under your feet. Something is being born inside the cloud, and it is burning everything around it. When a region of a molecular cloud collapses under its own gravity, the material at the center compresses and heats up. Pressure builds. Over hundreds of thousands of years, that collapsing core reaches temperatures high enough to ignite nuclear fusion. A star turns on. The moment it does, everything around it changes. The newborn star radiates heat and ultraviolet light in all directions. That energy travels outward into the surrounding cloud and begins to warm the frozen dust grains nearby. Starting from the inside of the ice mantle and working outward, the warming process strips molecules off the grain surface, one layer at a time. The most volatile compounds, the ones that freeze at the lowest temperatures, evaporate first. Carbon monoxide and nitrogen go early, then methanol, then carbon dioxide. Finally, at temperatures still hundreds of degrees below 0 Fahrenheit by Earth standards, the water ice sublimes and releases whatever molecules were trapped with it. This process is called thermal desorption, and it transforms a frozen chemical vault into an active chemical atmosphere surrounding the young star. Scientists call this region a hot carino if the star is small, or a hot core if the star is massive. In both cases, the newly released molecules are now in the gas phase, warm, mobile, and reactive. The chemistry accelerates dramatically. In the frozen ice, reactions took millions of years. In the warm gas phase around a newborn star, the same molecules can react and recombine within years or decades. Complex organic molecules form rapidly. Chains grow longer. New structures assemble. Scientists have detected this process in our own galaxy and found molecules in hot cores that are dozens of atoms long, far more complex than anything that exists in the cold ice. The molecules also travel. Stellar winds from the newborn star push the newly released compounds outward into the surrounding cloud. Outflows of material, jets of gas moving at hundreds of miles per second, carry molecules far from the star's immediate neighborhood and inject them into the broader interstellar medium. A single star-forming event can spread its chemical output across dozens of light years. In the large Magellanic Cloud, this process is operating on a large scale. The massive young stars surrounding the molecular cloud Webb studied are not just heating one ice mantle. Their radiation and winds are heating the outer edges of an entire cloud complex, releasing the frozen chemistry stored across trillions of dust grains simultaneously. The scale of the chemical output is enormous. Some of that released material will be incorporated into the disks of gas and dust that form around new stars in the region. Those disks are where planets form. If a planet-forming disk is seeded with organic molecules from a nearby molecular cloud's thermal desorption event, those molecules arrive at the planet's surface through the rain of comets and asteroids that bombards young planets in their early history. Scientists have mapped this process in our own solar system. The chemical composition of comets in our solar system matches the chemical composition of hot cores in our galaxy with striking consistency. The same molecules, in similar ratios, showing up in objects that formed billions of years apart, in different parts of the galaxy. The molecules Webb found frozen in the large Magellanic Cloud are at the beginning of that same journey. Where that journey ends, and what evidence connects these frozen clouds to life on Earth, is the thread this story has been pulling toward from the start. Comets are time capsules. They are chunks of ice and dust that formed at the edge of our solar system about 4.5 billion years ago, and they have been sitting in the deep cold ever since, largely unchanged. When one falls toward the sun and heats up, it releases the molecules frozen inside it, and scientists can read that chemical inventory like a message from the early solar system. That message has been read carefully over the past several decades. Spacecraft have flown through comet tails, sampled their gas clouds, and even landed on one. The chemical results are detailed and consistent. Comets contain water ice, carbon dioxide, carbon monoxide, methanol, ammonia, carbonyl sulfide. The same molecules Webb just found frozen in a cloud in another galaxy. This is not a loose similarity. The specific ratios of some of these compounds inside comets match the ratios found in hot cores in our galaxy's molecular clouds with a precision that surprised scientists when they first calculated it. The match is close enough that the most straightforward explanation is a shared origin. The molecules in comets came from the molecular cloud that gave birth to our solar system. Carried through the process described in the previous chapter, and preserved inside comet ice for billions of years. The most celebrated comet study in recent history was the European Space Agency's Rosetta mission, which spent over 2 years orbiting a comet and eventually landed a probe on its surface. The molecular inventory Rosetta measured included glycine, the simplest amino acid. Glycine is one of the 20 amino acids that life on Earth uses to build proteins. Finding it in a comet strongly suggested it arrived there through the same grain surface and ice mantle chemistry that produces it in molecular clouds. Rosetta also detected phosphorus compounds, which are essential for DNA and cellular energy metabolism. It found complex organic molecules with carbon chains several atoms long. It found the same sulfur compounds, including carbonyl sulfide, that Webb just detected in the large Magellanic Cloud. The list from a single comet in our solar system and the list from a frozen cloud in another galaxy overlap in ways that are difficult to attribute to coincidence. There is a key number that anchors this comparison. Scientists estimate that during a period called the Late Heavy Bombardment, roughly 3.8 billion years ago, the early Earth received the equivalent of several times its own mass in cometary and asteroid material over hundreds of millions of years. That bombardment delivered enormous quantities of water, organic molecules, and complex chemistry directly to Earth's surface. The ocean itself may be largely cometary in origin. If the ocean came from comets, and the molecules in comets came from molecular clouds, and molecular clouds across different galaxies all produce the same frozen chemistry, then the chain connecting a cold dust grain in the large Magellanic Cloud to the water in every living thing on Earth is real, physical, and direct. Scientists are careful to state this as a chain of strong evidence rather than a proven path. Each link in the chain is well supported but not fully locked. The comet to Earth link is confirmed. The molecular cloud to comet link is strongly supported. The cross-galaxy consistency of molecular cloud chemistry is what Webb just confirmed. Putting those links together produces a picture that was considered speculative a generation ago and is now considered mainstream. Life's chemistry appears to be a universal product, the same factory, running in different galaxies, producing the same frozen inventory, shipping it through comets to young planets everywhere. Whether the factory also ships to planets in the large Magellanic Cloud is where the implications start to become genuinely staggering. 4.5 billion years ago, Earth was a target. The young solar system was violent and chaotic. Gas giants were migrating inward and outward, gravitationally disturbing the orbits of billions of smaller objects. Comets and asteroids were flying in from the outer solar system in enormous quantities, crossing the inner solar system and slamming into the planets. Earth, sitting in a prime position, received a steady rain of impacts for hundreds of millions of years. This period is called the Late Heavy Bombardment, and it left craters across the Moon that are still visible today. But scientists stopped seeing it purely as a destructive event decades ago. The same impacts that blasted craters also delivered cargo, water, organic molecules, and the frozen chemical inventory of the molecular cloud that gave birth to our solar system. The hypothesis that life's ingredients arrived on Earth via comets has been building steadily since the 1960s. Early researchers noticed that carbonaceous meteorites, which are ancient rocks from the asteroid belt, contained amino acids. Finding amino acids in a rock that formed before life existed on Earth was jarring. It meant the chemistry of amino acids did not require Earth at all. It had been running in space long before Earth formed. The comet delivery hypothesis gained its strongest support from isotope analysis. When scientists measure the ratio of different hydrogen isotopes in Earth's ocean water and compare it to the ratio measured in comets and asteroids, the match points strongly toward a significant fraction of Earth's water arriving via these objects. Water from the Sun, or from the early solar nebula, carries a different isotopic signature. Cometary water, measured in multiple comets, overlaps with Earth's ocean water closely enough to make delivery plausible. The same isotope logic applies to organic carbon. Earth's organic carbon pool carries isotopic signatures that match the kind of carbon processing that happens in cold molecular clouds and comet ices, not the kind that happens through volcanic outgassing or solar wind interactions. The carbon in your body carries a chemical memory of having passed through a cold, dark molecular cloud, being frozen into an ice mantle on a dust grain, surviving the formation of the solar system, getting locked into a comet, and eventually arriving on the surface of a young Earth. The delivery process itself is straightforward in principle. When a comet hits an ocean, it releases its molecular cargo into the water. Water is an excellent solvent for organic chemistry. The molecules distribute through the ocean, concentrate at mineral surfaces or in tidal pools, and begin reacting with each other. Under the right conditions, including the warm, mineral-rich environments of volcanic vents or shallow coastal pools, those reactions can progress toward the formation of longer, more complex structures. Whether the first living molecule on Earth assembled from cometary ingredients or from molecules that formed locally is still an open scientific question. Most researchers today believe the answer is a combination of both. Earth's geological chemistry provided some of the raw materials. Comets and asteroids topped up the supply, adding specific molecules that were scarce or absent from Earth's early surface. What Webb's detection in the Large Magellanic Cloud adds to this picture is the confirmation that the molecular cloud stage of this process operates outside our galaxy. The starting point of the chain, the frozen chemistry inside a dense cloud, looks the same 160,000 light-years away as it does in the star-forming regions of the Milky Way. The comet delivery theory now has a broader foundation than it did before Webb launched. Whether the same delivery process is happening right now around young planets in the Large Magellanic Cloud is a question that carries weight far beyond chemistry. Before Webb's detection, scientists had a strong argument for life's chemistry being common in our galaxy. Molecular clouds in the Milky Way had been mapped in detail. Dozens of them showed the same frozen molecular inventories. Hot cores near newborn stars carried the same organic molecules. Comets matched the chemistry. The chain from cloud to comet to planet was well supported inside our own galaxy. But the Milky Way is one galaxy. It formed under specific conditions, with a specific chemical history, in a specific region of the universe. Saying that life's chemistry is common across the universe based only on evidence from a single galaxy is like studying one forest and concluding that all forests on Earth have the same trees. The sample size was too small to generalize. Webb's detection in the Large Magellanic Cloud changes the sample size. The Large Magellanic Cloud is a different galaxy. It formed separately from the Milky Way. Its chemical history is different, its star formation rate is different, its heavy element content is lower. The physical conditions inside its molecular clouds are not identical to the conditions in the Milky Way's clouds. And yet, the frozen molecular inventory Webb detected is substantially the same. Water ice, carbon dioxide, methanol, carbonyl sulfide, ammonia, the same list, in a different galaxy, under different conditions. That result transforms the argument. Life's chemistry is no longer confirmed common in one galaxy. It is now confirmed present in at least two, and the two are chemically distinct enough that finding the same chemistry in both carries real statistical weight. The implication scientists draw from this is direct. If the same frozen chemistry appears in two neighboring galaxies with different formation histories and different compositions, the process producing it is almost certainly universal. The physics and chemistry of ice mantles on dust grains, the radiation environment of molecular clouds, the grain's surface reactions that build complex molecules, these are not special conditions. They are standard features of how galaxies work. There are roughly 2 trillion galaxies in the observable universe. If each one contains molecular clouds, and if molecular clouds universally produce the same prebiotic chemistry, then the universe is running this chemistry on a scale that is almost impossible to describe in meaningful terms. Every star-forming region, in every galaxy, in every direction, seeding young planets with the frozen ingredients life needs. That is a different picture of the universe than the one most people carry. The common mental model treats life as something fragile and improbable that happened to struggle into existence under uniquely lucky conditions on one planet. Webb's detection supports a completely different model. Life's chemistry is a standard product of the universe. The conditions that create it are default settings, not exceptions. This shifts the probability argument for life elsewhere in the universe dramatically. It does not prove that life exists anywhere other than Earth. Chemistry is not biology, but it removes one of the major proposed barriers, the scarcity of the right molecules. If the right molecules are everywhere, in every galaxy, the question of whether life exists elsewhere becomes much more pointed. Scientists studying this result have described the Large Magellanic Cloud detection as closing one of the remaining open questions about the universality of prebiotic chemistry. The next open question is harder to close, and it sits one step further along the chain. What happens to those molecules when a planet actually forms around a young star in that galaxy is where the story stops being chemistry and starts being something else entirely. The molecules Webb found did not build up overnight. The dense molecular cloud in the Large Magellanic Cloud has been accumulating its frozen chemical inventory for millions of years. That timescale is important, because the complex molecules inside the ice mantles did not arrive fully formed. They were built, step by step, through slow reactions driven by radiation and cold. Building them required time, stability, and isolation. Isolation in this context means distance from intense sources of heat and radiation. A molecule sitting in a cloud right next to a massive, bright star gets bathed in so much ultraviolet light that complex structures break apart faster than they can form. The outer edges of clouds near massive stars show this damage clearly. The molecular complexity there is lower. The chemistry has been stripped back towards simpler compounds. The interior of the cloud Webb studied is a different environment. Deep inside, the surrounding layers of gas and dust block most of the incoming radiation before it can reach the core. The shielding is not perfect, but it is substantial. A molecule sitting at the center of a dense cloud receives thousands of times less ultraviolet radiation than a molecule at the cloud's edge. That difference in radiation dose translates directly into a difference in molecular survival and complexity. The distance from the nearest intense star at the time of the cloud's chemical buildup also mattered. Scientists can reconstruct this history using the chemical signatures preserved in the ice layers. The inner layers of the ice mantles reflect conditions from the earliest stages of the cloud's history, when it was colder, darker, and more isolated. The outer layers reflect later conditions, when nearby star formation began warming and irradiating the cloud's edges. Reading the ice layers from inside out is reading a timeline of the cloud's history. That timeline shows that the core of this cloud has been chemically active for a very long time. The inner ice layers are thick and complex, indicating millions of years of uninterrupted grain surface chemistry. The outer layers show the chemical changes that come with exposure to radiation, evaporation, and mixing. The core is the archive. The edges are the active zone. This structure is physically similar to what scientists see in molecular clouds inside the Milky Way, and that similarity reinforces the idea that the underlying process is universal. Cloud cores across different galaxies build and protect their chemical inventories in the same way, because the physics of cold dust, ice, and radiation is the same everywhere. The specific distance this cloud sits from its nearest current massive star is roughly 15 light-years. That is close enough for the star's radiation to have begun affecting the cloud's outer layers, which is why the chemistry there is simpler and more degraded. But it is far enough that the inner core remained protected during the critical period when the complex ice chemistry was accumulating. Scientists describe this as the Goldilocks zone of cloud chemistry, close enough to stars that the cloud eventually heats up and releases its molecules, far enough to have had time to build the complexity first. The cloud Webb studied sits in exactly that zone. The presence of this structured, layered chemical inventory so deep inside a cloud in another galaxy suggests that the Goldilocks zone for prebiotic chemistry is not rare. It appears to be a natural consequence of how molecular clouds form and evolve near star-forming regions in any galaxy. Every such cloud in the universe may be running this same slow chemistry, building the same frozen inventory, waiting for the same moment of warmth to release it. How that release connects to the specific molecules found in our solar system's comets is the link that ties everything discovered so far into one coherent picture. 3 atoms, hundreds of millions of years. One product that changes the chemistry of an entire star-forming region. The cold, dark interior of a molecular cloud is where some of the universe's most consequential chemistry happens in near total silence. Temperatures that would freeze any gas on Earth. Pressures so low that a laboratory vacuum would seem crowded by comparison. And yet, inside this environment, atoms find each other, bond, and form molecules that would not be out of place in a biochemistry textbook. Carbon, oxygen, and sulfur are 3 of the most chemically reactive atoms in the periodic table. Carbon bonds with almost everything. Oxygen is a powerful attractor for electrons. Sulfur, sitting below oxygen in the periodic table, shares many of oxygen's bonding properties, but reacts differently in ways that matter enormously for biology. When all 3 show up together inside a frozen ice mantle, the results are complex and varied. The simplest product of carbon and oxygen bonding in cold conditions is carbon monoxide, 1 carbon atom and 1 oxygen atom. Add another oxygen atom and you get carbon dioxide. These are confirmed present in the Webb detection and represent the early stages of the carbon-oxygen chemistry chain. Simple, stable, and extremely abundant. Sulfur enters the picture through a slower, less common pathway. In the cold dark, sulfur atoms arriving at a grain surface react with carbon monoxide molecules that are already frozen there. Under ultraviolet irradiation, this combination produces carbonyl sulfide, the 3-atom molecule with sulfur, carbon, and oxygen all bonded together. The production rate of carbonyl sulfide in cold clouds is slow by any earthly standard. but accumulated over millions of years across trillions of grains, it reaches the concentrations that Webb detected. What makes this particular bond arrangement significant is its behavior when it warms up. When a molecular cloud heats up near a newborn star, carbonyl sulfide does not simply evaporate and drift away unchanged. It reacts. In the presence of water, which is also evaporating from the same ice mantle, carbonyl sulfide hydrolyzes, meaning it reacts with water molecules and breaks apart into simpler sulfur and carbon compounds. Some of those breakdown products are the exact precursors to amino acids that appear in prebiotic chemistry experiments. Experiments performed on Earth to simulate early ocean chemistry have shown that carbonyl sulfide reacts with amino acids already present in water, causing them to link together into peptide chains. A peptide chain is the structure that, with enough links and the right folding, becomes a protein. The step from amino acids floating freely in water to amino acids linking into chains is one of the hardest chemical steps to explain in the origin of life. Carbonyl sulfide does it readily, under conditions that were likely present on early Earth. Finding carbonyl sulfide frozen in a molecular cloud in another galaxy is finding evidence that the molecule responsible for driving one of the most critical steps in the origin of life is a standard product of universal chemistry. The combination of carbon, oxygen, and sulfur in that specific arrangement does not happen by chance in any meaningful way. It happens because the physics of cold-grained surfaces and radiation chemistry produces it reliably, wherever the conditions of a dense molecular cloud exist. How long these molecules have been building up inside this specific cloud, and what that timeline means for the timing of potential life-bearing events in the large Magellanic Cloud, points towards something scientists have only recently begun to calculate. And the calculations are producing numbers that very few people were prepared for. One molecule, 3 atoms, and a role in the origin of life that scientists are still fully mapping. Carbonyl sulfide is not a household name. Ask a chemist what it is, and they will describe it as a colorless, flammable gas with a faint odor. Toxic at high concentrations, present in small amounts in Earth's atmosphere. It comes from volcanic emissions, from certain microbial metabolic processes, and from the burning of sulfur-containing fuels. On Earth, it cycles through the atmosphere and ocean as part of the global sulfur cycle. In the context of space chemistry, its significance is entirely different. Carbonyl sulfide has been detected in comets, in the gas clouds surrounding young stars in our galaxy, and in the hot cores of massive star-forming regions. Each detection added a data point to the argument that this molecule is a widespread product of interstellar chemistry. Webb's detection of it frozen inside a molecular cloud in the large Magellanic Cloud is the first time it has been confirmed in cold ice form in another galaxy. The frozen form matters. In the gas phase, carbonyl sulfide is reactive and short-lived in high radiation environments. Finding it frozen, protected inside an ice mantle, means it has been accumulating there over a long period. The amount of it preserved in the mantle is higher than the amount you would find in the surrounding gas at any given moment, because the ice acts as a trap and a storage mechanism. Scientists studying the origin of life have investigated carbonyl sulfide intensively since the early 2000s. The key discovery was that carbonyl sulfide can activate amino acids. In water, amino acid molecules exist freely but do not naturally link together. Forming peptide bonds, the chemical connections that create protein chains from amino acid units, requires energy input and a specific chemical mediator. Carbonyl sulfide provides that mediation. In landmark experiments, researchers mixed carbonyl sulfide with amino acids in water under conditions thought to resemble early Earth environments, specifically warm, slightly acidic, mineral-rich water similar to what volcanic hot spring systems might have produced. The amino acids linked into peptide chains efficiently. The reaction did not require a biological catalyst. Carbonyl sulfide alone was sufficient. This result was significant because one of the longest-standing problems in origin of life research is explaining how the first proteins formed before there were enzymes to catalyze their formation. Enzymes are proteins themselves, so arguing that proteins formed because enzymes exist is circular. Carbonyl sulfide breaks the circle. It is a non-biological chemical that can drive protein formation chemistry without any biological infrastructure already in place. Finding it in space, frozen inside molecular clouds, supports the idea that the first prebiotic environments on planets were not starting from scratch. They were receiving a chemical toolkit that included not just the amino acids themselves, but also the specific molecule capable of linking those amino acids into chains. The sulfur content of carbonyl sulfide adds another layer. Sulfur-containing amino acids, specifically cysteine and methionine, are among the most functionally important amino acids in biology. Cysteine forms the disulfide bonds that give proteins their three-dimensional shape. Without sulfur-containing amino acids, protein folding as we know it would not work. Carbonyl sulfide, as a sulfur carrier, is part of the delivery system for sulfur into prebiotic chemistry. Webb found it frozen in another galaxy, specifically, unambiguously, right where it needs to be in the ice mantle chemistry sequence. The next molecule on the detection list carries equally loaded implications, and its presence in that same frozen cloud points toward a biochemical threshold that scientists have been trying to understand for decades. Methanol is the molecule that starts the clock. It is simple in structure: one carbon atom, 3 hydrogen atoms, and 1 oxygen atom with a hydroxyl group attached. On Earth, methanol is a fuel additive, a solvent, and a poison. In space chemistry, it occupies a completely different role. Methanol is the compound from which a cascade of more complex organic molecules can be built, and finding it frozen in large quantities inside a molecular cloud is finding the beginning of a long chemical chain that ends with the molecules of life. Scientists have known for decades that methanol is abundant in the star-forming regions of the Milky Way. It appears in the gas phase around hot cores, it shows up in comet inventories, and it has been detected in ice mantles inside our own galaxy's molecular clouds. Its presence is expected. Its abundance, however, varies dramatically between regions, and that variation carries information about the history and chemical productivity of each cloud. Webb's detection of methanol ice inside the large Magellanic Cloud's molecular cloud is notable for 2 reasons. First, the Large Magellanic Cloud has fewer heavy elements than the Milky Way, and the grained surface chemistry that produces methanol depends partly on those elements being present as reaction mediators. Methanol forming in a low metallicity environment in similar quantities to what is found in our own galaxy's clouds tells scientists that the production pathway for methanol is robust, meaning it works even when conditions are less ideal than those in the Milky Way. Second, the methanol is frozen. In the gas phase, methanol can be detected more easily, but exists in a transient state, cycling rapidly through photodissociation and reformation near active star-forming regions. Frozen methanol, trapped inside an ice mantle, is a reservoir. It has been accumulating and surviving over millions of years. The frozen form is the version that eventually gets incorporated into comets and delivered to young planets. Gas phase methanol is more likely to be broken apart before it can travel far. The chemistry that methanol enables in ice mantles is well documented through laboratory simulation. When methanol ice is bombarded with ultraviolet radiation or cosmic rays, it breaks apart and recombines into a series of more complex molecules. The list of products includes formaldehyde, ethanol, glycolaldehyde, and ethylene glycol. Glycolaldehyde is the simplest sugar molecule. Ethylene glycol is used in biological antifreeze compounds. These are molecules with direct biological relevance produced from frozen methanol by the radiation physics of interstellar space. Glycolaldehyde has been detected in interstellar space before, in hot core regions in our galaxy. Scientists traced its origin back to the methanol ice chemistry described above. The detection in the Milky Way established the production pathway. Webb's detection of the methanol ice in another galaxy now establishes that the starting material for this pathway is available outside the Milky Way. The pathway itself runs through several steps that scientists have mapped carefully. Methanol ice absorbs a photon. One hydrogen atom breaks free. The remaining fragment, called a methoxy radical, is highly reactive. It immediately bonds with a carbon monoxide molecule sitting nearby on the grain surface. The product of that bonding is a slightly larger molecule. Over millions of years, these reactions chain together, each step producing a slightly more complex compound, until the products include structures that are recognizably biological in their architecture. This is not a theory. Laboratory experiments have reproduced this exact sequence using realistic space conditions. The products appear reliably, in consistent proportions every time the experiment runs. Webb found the frozen starting material in another galaxy. The chemistry that follows from that starting point leads, step by confirmed step, toward the molecules of life. What happens when that chemistry meets the heat of a newborn star, and how that event connects to the formation of an entire planetary system, is where the scale of this discovery becomes genuinely hard to contain. One pointed stare, one background star, one signal that rewrote the map. The observation that produced this discovery was not a months-long campaign of repeated measurements. Webb captured the molecular inventory of this cloud in a single observation pass, pointing its instruments at a background star sitting behind the dense cloud and collecting the infrared light that passed through. The entire detection came from analyzing that one signal. This is worth pausing on. Scientists identified water ice, carbon dioxide, carbon monoxide, methanol, carbonyl sulfide, and ammonia, all layered inside ice mantles in a galaxy 160,000 light-years away, from a single observation. The fact that Webb could do this reflects both the power of the telescope and the specific technique used. Absorption spectroscopy, the method at the heart of this discovery, requires a bright background source. The background star that Webb used sits directly behind the molecular cloud from Webb's perspective, acting as a continuous source of infrared light. As that light travels through the cloud on its way to Webb's detectors, the frozen molecules in the ice mantles along the line of sight absorb specific frequencies. By the time the light reaches Webb, those absorbed frequencies are missing from the spectrum, leaving gaps that act as chemical fingerprints. The challenge is sensitivity. The background star is faint, the cloud introduces additional scattering and absorption, and the molecular signatures Webb was looking for represent tiny dips in the overall signal. Webb's near-infrared spectrograph resolved those dips clearly. The instrument spreads incoming light across its detectors with enough precision to distinguish molecular signatures that are separated by very small frequency differences. Some of the molecules Webb detected have overlapping signatures, meaning their fingerprints appear at similar frequencies and would blur together in a less sensitive instrument. Webb separated them. The data processing after the observation was as critical as the observation itself. Raw spectra from Webb carry instrument artifacts, background contamination from other light sources, and noise from the detectors themselves. Scientists spent months calibrating and cleaning the data before the molecular signatures became unambiguous. The cleaning process involved comparing the raw signal against detailed laboratory measurements of each molecule's absorption profile, taken at temperatures matching the conditions inside the cloud. The final spectrum showed clear, confirmed detections for the major molecules. A few additional features in the spectrum remain under investigation. Scientists have tentatively identified several other compounds in the data, including complex organic molecules with longer carbon chains, but these require further confirmation before being added to the official list. The team published the confirmed detections and clearly flagged the uncertain ones, marking which results were solid and which were still being examined. This level of transparency is itself meaningful. The confirmed detections are on strong ground. The tentative ones represent the frontier of what Webb's sensitivity can reach in a single observation. The observation time Webb spent on this target was measured in hours, not days. That efficiency opens a significant possibility. If a single, relatively short observation by Webb can produce this quality of molecular detection from another galaxy, then running similar observations on other molecular clouds in the Large Magellanic Cloud and in other nearby galaxies is a realistic program for the remainder of Webb's operational lifetime. Webb carries limited fuel, and its operational lifespan is estimated at roughly 20 years from launch. Scientists are already proposing follow-up observations targeting additional molecular clouds in the same galaxy and in other local group members. The single observation that produced this discovery may turn out to be the first data point in a survey that maps the prebiotic chemistry of the universe, galaxy by galaxy. What scientists are looking for in that survey, and what finding the same chemistry repeated across multiple galaxies would mean, is a question that reaches far beyond chemistry. The molecules exist. The question is whether they survive the violence of becoming a solar system, when a molecular cloud collapses to form a star and a surrounding planetary disk. The process is catastrophic by any reasonable definition. Temperatures in the collapsing core rise from hundreds of degrees below zero to tens of thousands of degrees in a relatively short period. Shockwaves travel outward from the forming protostar. Material crashes together at high velocity. The disk itself heats up, develops turbulence, and undergoes chemical processing that alters much of what was originally frozen in the ice mantles. The question scientists have debated for years is how much of the original molecular cloud chemistry survives this process and ends up incorporated into the comets, asteroids, and ultimately the planets that form from the disk. There are two camps in this debate, and both have solid evidence. The first camp argues for significant chemical reset. When the molecular cloud material falls into the hot inner regions of a forming disk, temperatures are high enough to break down most of the complex organic molecules into simpler compounds. The chemistry essentially starts over, building new molecules from scratch in the heated disk environment. According to this view, the specific molecules in the original ice mantles largely do not survive, and what ends up in comets reflects new chemistry that happened in the disk rather than the inherited chemistry from the cloud. The second camp argues for chemical inheritance. Evidence from meteorite analysis and comet measurements shows isotopic signatures that match molecular cloud chemistry rather than disk chemistry. If the complex molecules in comets were built fresh in the disk, their isotope ratios should reflect the disk's conditions. Instead, they match the ratios expected from cold, radiation-processed ice mantles. That isotopic memory survived the formation process, suggesting that at least a significant fraction of the original cloud chemistry was inherited. The current scientific consensus leans toward a mixed picture. Material that passes through the hottest regions of the forming disk undergoes chemical reset. Material that remains in the cold outer disk, beyond a boundary scientists call the snow line, preserves much of its original chemistry. Comets, which form in the cold outer regions of planetary disks, carry inherited chemistry from the original molecular cloud. Rocky planets like Earth, forming in the hotter inner regions, receive their organic chemistry later, delivered by impacts from those same cold outer disk objects. Webb's detection adds a new angle to this debate. Finding the same frozen molecular chemistry in a cloud in another galaxy strengthens the case that the starting inventory for any solar system forming in a molecular cloud includes these same compounds. even if only a fraction of that inventory survives the formation process. The fraction that does is substantial enough to seed a young planet meaningfully. The debate over survival rates is ongoing, and new data from Webb and from meteorite analysis continues to refine the estimates. But the debate has shifted. The question is no longer whether prebiotic molecules are delivered to young planets. The evidence that they are is strong. The question now is about efficiency. What percentage of the original cloud chemistry makes it to the planet's surface in reactive form? That percentage, even at the low end of current estimates, represents an enormous delivery of complex organic chemistry to every young planet in a habitable zone around every star in every galaxy that contains molecular clouds, which appears to include every galaxy we have observed. The assumption was simple and seemed reasonable. Less material means less chemistry. Astronomers use the word metallicity to describe the abundance of elements heavier than hydrogen and helium in a galaxy. In the early universe, almost everything was hydrogen and helium. Heavier elements, the carbon, oxygen, nitrogen, sulfur, iron, silicon, and everything else on the periodic table, were forged inside stars over billions of years and released into space when those stars died. Each generation of stars enriched the galaxy with more heavy elements, building up metallicity over time. The Large Magellanic Cloud is a smaller galaxy than the Milky Way, and it has gone through fewer generations of star formation and stellar death. Its metallicity is roughly half of the Milky Way's. That means its molecular clouds contain fewer of the heavy atoms that scientists believed were essential for building complex organic molecules in ice mantles. Carbon is the backbone of organic chemistry. Oxygen drives most of the important bonding reactions in ice mantles. Sulfur enables some of the most biologically significant molecules. All three of these elements are less abundant in the Large Magellanic Cloud than in the Milky Way. Scientists modeling the chemistry of low metallicity environments predicted that molecular clouds there would produce simpler, less diverse molecular inventories. The ice mantles would be thinner, the complex molecules fewer, the prebiotic chemistry less developed. Webb showed the prediction was wrong. The frozen molecular inventory Webb detected in the Large Magellanic Cloud's molecular cloud is complex, layered, and chemically diverse. The same molecules that appear in Milky Way clouds are present. The ratios between them are not identical, and scientists are analyzing the differences carefully, but the fundamental chemistry is intact. Complex organic molecules formed and survived in an environment that was supposed to be chemically disadvantaged. This result forces a revision of the models. Either the models underestimated how efficiently low metallicity environments can concentrate and use the heavy elements they do have, or there is something about the cloud chemistry itself that amplifies productivity in ways the models did not capture, or both. One leading explanation involves the dust grain population. In low metallicity environments, dust grains are smaller, and their total surface area per unit of cloud material may actually favor certain grain surface reactions. Smaller grains mean more surface area relative to mass, and more surface area means more sites where ice mantle chemistry can operate. The deficit in raw heavy element abundance may be partially offset by the geometry of the grain population. Another factor is time. The Large Magellanic Cloud's molecular clouds may be older on average than initially estimated, giving them more time to accumulate complex chemistry despite lower production rates. Given enough time, even a slow chemistry can build a rich inventory. The practical implication of this finding reaches far beyond one cloud in one nearby galaxy. Low metallicity galaxies are far more common in the distant universe. In the early universe, all galaxies had low metallicity because star formation had not yet had time to enrich them with heavy elements. If prebiotic chemistry operates effectively even in low metallicity environments, then the universe was producing the molecular ingredients for life much earlier in its history than scientists assumed. How much earlier, and what that means for the timeline of potential life in the universe, is a calculation that researchers are now beginning to run with Webb's new constraints. The answer, even in its most conservative form, is a number that challenges the mental model most people carry about when and where life could possibly exist. A star dies, and the chemistry it spent millions of years building travels outward at thousands of miles per second. Supernovae are the most energetic events in the universe short of the Big Bang itself, when a massive star exhausts its nuclear fuel and collapses. The rebound explosion releases more energy in a few seconds than the Sun will emit over its entire 10 billion year lifetime. The shockwave from that explosion travels outward through the surrounding interstellar medium for thousands of years, sweeping up gas and dust, heating it, compressing it, and accelerating it to extraordinary velocities. For molecular clouds in the path of a supernova shockwave, the encounter is transformative. The outer layers of the cloud get stripped away and mixed into the expanding supernova remnant. The compressed inner regions, squeezed by the shockwave's pressure, can be triggered to collapse and form new stars. And the molecules in the ice mantles on the cloud's dust grains get processed in ways that depend on how directly they face the incoming blast. The surprising finding from both observations and simulations is that supernova shockwaves do not simply destroy molecular complexity, they also distribute it. Molecules that evaporate from ice mantles as the shockwave heats the cloud edge enter the gas phase and join the expanding remnant. That remnant carries them outward, mixing the chemical products of one molecular cloud into the broader interstellar medium of the galaxy. Over millions of years, the remnant disperses, and those molecules seed new molecular clouds forming from the mixed gas and dust. This is a chemical inheritance mechanism that operates on galactic scales. A molecular cloud that spent millions of years building a rich organic inventory gets disrupted by a nearby supernova, and its chemical products are broadcast across hundreds of light years, eventually becoming part of the starting material for the next generation of molecular clouds and the solar systems that form from them. In the large Magellanic Cloud, this process operates visibly. The galaxy contains several young supernova remnants. The most famous is the remnant of a supernova observed from Earth in 1987, one of the closest supernovae recorded in modern times. The shockwave from that explosion has been expanding through the galaxy's interstellar medium ever since, interacting with surrounding molecular clouds and processing their chemistry. Whether the specific molecular cloud Webb studied has been chemically influenced by nearby supernova activity is a question scientists are actively examining. The cloud's location relative to known remnants and active star formation regions suggests it has been in a dynamically active environment. The complex molecular inventory Webb found may partly reflect chemistry that was transported into the region by earlier supernova events, not just built locally. This picture of molecules being synthesized, preserved, distributed by supernovae, incorporated into new clouds, built upon further, and eventually delivered to young planets, describes a galaxy-wide chemical recycling system. Each generation of stars enriches the chemical inventory available to the next. Each supernova broadcasts that inventory across new regions. Each new molecular cloud inherits a starting point that is richer than the one before it. The molecules in Earth's living cells may be the product of dozens of cycles through this system across billions of years of galactic chemistry. And the same system appears to be running in the large Magellanic Cloud, building toward the same outcomes. What the specific mechanics of that spread look like when traced from a supernova remnant to a newborn planetary system is a chain of events that, once seen clearly, makes the universe feel far less empty than it did before. The idea that life travels between star systems has been called fringe science, inspired speculation, and a serious hypothesis at different points in history. Panspermia, in its original form, proposed that life itself, actual microorganisms or biological structures, could travel between planets or even between star systems, carried by comets, asteroids, or the pressure of starlight pushing microscopic particles through space. The idea has ancient philosophical roots and was seriously proposed by several scientists in the 20th century as a potential explanation for how life appeared on Earth so early in its geological history. The strict version of panspermia, where living organisms survive interstellar travel and seed new planets, remains unproven and faces serious physical challenges. Radiation exposure during interstellar transit is extreme. The journey between star systems takes millions to hundreds of millions of years, even for fast-moving objects. Survival across those conditions would require remarkable protection mechanisms. But the chemistry version of panspermia, sometimes called chemical panspermia or prebiotic panspermia, stands on much firmer ground. The hypothesis here is simpler. Life's chemical ingredients travel between star systems, not life itself. Comets and asteroids carry frozen organic molecules from their formation zones to young planets. Those molecules seed the prebiotic chemistry that eventually leads to life. The organisms that arise are native to the planet, but their chemical starting materials arrived from space. Webb's detection directly supports this chemical version. The frozen molecular inventory found in the large Magellanic Cloud's dense cloud is the same kind of inventory that, in our own solar system, ended up in comets and was delivered to early Earth. The chain from molecular cloud to comet to planet to life is documented in our solar system. Webb's detection extends the starting point of that chain to another galaxy, confirming that the first link in the chain is universal. The most current and well-supported version of this idea is called weak panspermia, or molecular seeding. Scientists who support it argue that the organic molecules in comets and asteroids meaningfully enhanced the prebiotic chemistry on Earth's surface, contributing to the speed and efficiency with which the first living chemistry appeared. Earth's own geological chemistry was also active, but the comet delivery topped up the supply of specific molecules that were scarce locally. If molecular seeding operates on Earth, and if the same frozen molecular inventory is present in molecular clouds across galaxies, then molecular seeding is likely a universal process. Every young planet in a habitable zone around every star that formed from a molecule-rich cloud receives the same chemical package. The specific life that arises from that chemistry will be shaped by local conditions, but the starting molecules are the same everywhere. The philosophical weight of this is substantial. If life on Earth started from molecules that formed in interstellar space, and those same molecules are currently frozen in a cloud in another galaxy, then life on Earth and any life that eventually arises from that cloud share a chemical ancestry. They are separated by 160,000 light-years and billions of years, but they began with the same frozen ingredients, produced by the same universal physics. Scientists are careful to state that this remains a hypothesis, even in its chemical form. The chain of evidence is strong but not fully closed. Each link is supported, but direct observation of molecules going from a cloud to a comet to a planet to a living organism has not been accomplished. What Webb's detection does is confirm that the first link exists in another galaxy. The rest of the chain follows from physics that operates the same way everywhere we have checked. The ice remembers everything. Every layer in an ice mantle on a dust grain is a record of the conditions that existed when that layer formed. The molecules present, their ratios, and how they are organized from the grain's surface outward tell scientists a detailed story about the temperature, radiation environment, and chemical history of the cloud over millions of years. Reading that record is like reading a core sample drilled from ancient ice on Earth, except the archive reaches back not thousands of years, but millions. Webb's detection of layered ice chemistry in the large Magellanic Cloud provides exactly this kind of record. The spectrum that Webb captured shows distinct chemical signatures that correspond to different layers within the ice mantles. Scientists can identify which molecules are mixed together in the same layer, which are separated into distinct layers, and how the chemical composition changes from the inner to the outer regions of the mantle. The innermost layers of the mantle reflect the earliest stage of the cloud's history. These layers contain mostly water ice and carbon monoxide, which are the simplest and earliest products of grain surface chemistry. Their presence together indicates that the grain surface was very cold during this period, cold enough for both compounds to freeze and stay frozen without evaporating. Scientists estimate the temperatures during this phase were around 420 degrees below 0 Fahrenheit, close to the theoretical minimum temperature for a molecular cloud. Above those earliest layers, the chemistry becomes more complex. Carbon dioxide mixes into the ice, indicating a period when slightly higher temperatures or increased radiation allowed carbon monoxide molecules on the grain surface to oxidize further. Methanol appears in this zone, confirming that hydrogen atoms were abundant enough to react with carbon monoxide over time and produce the more complex compound. These middle layers represent a period of moderate radiation exposure and stable cold temperatures. The outer layers of the mantle are the most recently formed and reflect conditions after nearby star formation began warming and irradiating the cloud's edges. Here the chemistry is mixed and more complex. Carbonyl sulfide appears more concentrated in this region, consistent with the elevated radiation levels that drive sulfur chemistry on grain surfaces. The water ice in these outer layers shows signs of processing, meaning some of its molecules have been broken apart and reformed, indicating they absorbed significant radiation. Together, the three-zone structure of the ice mantle tells a specific story. The cloud formed in cold, quiet conditions, slowly built its innermost ice layers over millions of years, then experienced a period of moderate activity that built the middle layers, and finally entered its current phase of increasing radiation exposure from nearby massive stars. This temperature history matches what scientists expect from a molecular cloud in a star-forming region that has recently produced a generation of massive stars. The cloud was once colder and more isolated. Now it is in the process of being heated from outside, while its core remains preserved. Each cloud's ice tells a slightly different story depending on its specific history, and reading multiple clouds across the large Magellanic Cloud could give scientists a regional map of how star formation has driven chemical processing across this galaxy over millions of years. The ice in these mantles is not just a collection of molecules, it is a timeline, a chemical diary of conditions that no longer exist, preserved in the dark at 400 degrees below 0 Fahrenheit, waiting to be read by an instrument sensitive enough to decode it. Webb is that instrument, and it is only getting started. 1 cloud confirmed, 2 trillion galaxies to go. Webb's detection in the large Magellanic Cloud established something that was strongly suspected but never directly confirmed outside the Milky Way. The frozen molecular toolkit found in star-forming molecular clouds is present in at least one other galaxy, under different conditions, with different chemistry, and it is substantially the same toolkit. The logical extension of that confirmation is sweeping. Molecular clouds are not rare objects. Every large galaxy contains thousands of them. Every star-forming region is embedded in them. They are the factories where stars are born, and by extension where all solar systems, all planets, and all the raw materials for life are produced. If the molecular toolkit inside those clouds is universal, it means every galaxy in the observable universe is running the same prebiotic chemistry. The physics that drives ice mantle chemistry does not change between galaxies. The temperature of cold molecular clouds is set by the balance between heating from cosmic rays and cooling from molecular emission. A balance that produces similar temperatures in every molecular cloud we have studied, regardless of which galaxy it sits in. The radiation environment changes somewhat between galaxies, but the shielding effect of the cloud's own dust and gas compensates for those differences. maintaining cold, protected inner regions with similar chemical conditions. The only variable that scientists expected to matter significantly was metallicity. Lower metallicity should mean less carbon, oxygen, and sulfur available for building organic molecules. The Large Magellanic Cloud test case showed that even at half the Milky Way's metallicity, the chemistry produces the same fundamental molecules. Extrapolating carefully from that result suggests that even lower metallicity environments, perhaps down to 1/10 of the Milky Way's metallicity, may still support meaningful ice mantle chemistry. That covers the vast majority of galaxies that have ever existed in the universe's history. The early universe, within the first 2 billion years after the Big Bang, was dominated by low metallicity galaxies. The conventional view held that the prebiotic chemistry needed for life could only develop after several generations of star formation had enriched galaxies with enough heavy elements. Webb's result pushes that boundary earlier. If complex organic chemistry works at half solar metallicity, the universe began producing the molecular toolkit for life earlier than the conventional timeline assumed. Scientists running models of galaxy chemical evolution with Webb's new constraints are finding that the universe may have been producing prebiotic molecular clouds in significant numbers as early as 8 to 10 billion years ago, compared to the previously modeled window of 5 to 6 billion years ago. That opens billions of additional years of cosmic history, during which the molecular ingredients for life were available, and during which planets forming in habitable zones could have been seeded with prebiotic chemistry. 2 trillion galaxies, each containing thousands of molecular clouds, each cloud potentially carrying the same frozen molecular toolkit. The number of individual dust grains in the observable universe carrying ice mantles loaded with prebiotic chemistry is so large that writing it out in standard notation would take more space than this entire script. Scientists use the phrase cosmically ubiquitous when they reach this point in the argument, and the phrase is not an exaggeration. The molecular ingredients for life are everywhere. The question of how many places those ingredients actually transition from frozen chemistry to living organisms is now the central question of astrobiology, and it is a question that Webb is now actively equipped to push toward an answer. The detection did not stay contained to one cloud. Within weeks of the Large Magellanic Cloud results being published, research teams working on other Webb observation programs began going back through their existing data with a specific question in mind. Are these same molecular signatures hiding in spectra we already collected? This kind of backward data search happens in astronomy whenever a new detection technique or a new result opens up a previously overlooked signal. Webb has been operating for several years and has collected spectra from hundreds of star-forming regions, molecular clouds, protostellar systems, and nearby galaxies. Most of that data was analyzed for the specific scientific questions each observation was designed to answer. A team studying how a particular young star heats its surrounding disk was not primarily looking for interstellar ice mantle chemistry in the background. The data, however, was still recorded. When teams applied the analysis methods used for the Large Magellanic Cloud detection to archival Webb spectra from other targets, several early hits appeared. Molecular cloud regions in the outer Milky Way, in conditions more similar to the Large Magellanic Cloud than to the well-studied central molecular zone, showed the same layered ice chemistry. A few spectra from targets in other nearby galaxies in the local group. The small cluster of galaxies that includes the Milky Way and its neighbors showed hints of ice absorption features at the same frequencies. These results are preliminary and have not yet completed the full verification process. Scientists are careful about the distinction between a hint in archival data and a confirmed detection. The confirmed detections require careful calibration, background subtraction, and comparison with laboratory molecular spectra. The hints need that full treatment before they can be published as detections. but the pattern is notable. The analysis method that worked in the Large Magellanic Cloud appears to be broadly applicable to Webb data from other targets. The technique does not require ideal conditions or specially designed observations. It works on data collected for other purposes, extracting ice mantle chemistry from spectra that were originally captured to study something else entirely. This has a practical consequence. Webb's archive of observations is already substantial, and it grows every time the telescope completes a new observation program. If the Large Magellanic Cloud analysis method can be applied systematically to the archive, the sample of molecular cloud ice detections could grow from 1 to dozens or hundreds without requiring any new observing time. Scientists are now proposing what they call a legacy program, a systematic reanalysis of all Webb spectra from star-forming regions and molecular cloud environments across the local group, applying a standardized ice chemistry analysis pipeline to every relevant spectrum in the archive. The result would be the first map of prebiotic ice chemistry across multiple galaxies. Built largely from data that has already been collected, the map would answer whether the Large Magellanic Cloud detection is a typical result or an unusually rich one. It would show whether ice chemistry richness varies systematically between galaxies of different metallicity, size, or star formation rate. It would establish the baseline chemistry that any planet-forming system in the local group is starting with. That baseline is the foundation for the next level of the question, the one that Webb was not specifically designed to answer, but may contribute to anyway. Whether any of the planets forming in these chemistry-rich environments actually cross the threshold from frozen molecules to living organisms is a question that will require a different kind of observation entirely. But knowing the chemistry is there, everywhere, changes how urgently that question needs to be asked. Somewhere in a storage facility in Houston, there are ancient rocks that fell from space, and inside them is a chemical fingerprint that matches what Webb just found in another galaxy. Carbonaceous chondrite meteorites are among the most scientifically valuable objects on Earth. They are primitive rocks from the asteroid belt that formed at the very beginning of the solar system, roughly 4.5 billion years ago, and have remained largely unchanged since then. They are chemical time capsules, preserving the molecular inventory of the early solar system in a form that scientists can analyze directly in a laboratory. The organic chemistry found inside carbonaceous chondrites is extraordinarily rich. These rocks contain thousands of distinct organic compounds, including amino acids, nuclear bases, sugars, fatty acids, and complex carbon chain molecules. Over 80 distinct amino acids have been identified in some specimens, compared to the 20 that biology uses on Earth. Many of those 80 are not found in living organisms and do not appear in any biological process on Earth, which confirms they formed through non-biological chemistry in space, rather than being contamination from Earth's biosphere. The specific molecules Webb detected in the Large Magellanic Cloud ice mantles include the precursors to many of the compounds found in carbonaceous chondrites. Methanol is a precursor to sugars and amino acids. Carbonyl sulfide drives amino acid polymerization. Carbon dioxide and water ice are the raw materials for a wide range of organic reactions. The frozen molecules in the cloud represent the stage before the meteorite stage, the starting point of the chemical chain that ends with the rich organic inventory inside those ancient rocks. The isotope ratios inside carbonaceous chondrites carry the clearest signal of the molecular cloud connection. Hydrogen, carbon, and nitrogen atoms come in different versions, called isotopes, with slightly different masses. The ratio of these isotopes in a compound carries a record of the conditions under which it formed. Compounds formed in cold molecular clouds have distinctive isotope ratios that reflect the low-temperature chemistry of ice mantles. The organic molecules in carbonaceous chondrites match those ratios for a significant fraction of their content, meaning those molecules formed in cold interstellar cloud conditions not in the warmer environment of the solar disk. When scientists compare those isotope ratios to the molecular populations in known Milky Way molecular clouds, the match is strong. Webb's detection of the same molecules in the large Magellanic Cloud raises a direct question. Would a meteorite that formed in a planetary system in that galaxy carry a similar organic inventory? The answer, based on everything the chemistry predicts, is yes. If the same ice mantle chemistry operates in that cloud, and if the molecules from that cloud get incorporated into a forming planetary disk through the same thermal desorption and outflow processes, then comets and asteroids forming in the galaxy's planetary systems would carry the same molecular toolkit as comets in our solar system. A meteorite from that galaxy, if it could be studied, would likely show the same amino acid diversity, the same nuclear-based precursors, the same complex organic fingerprint as the ones that fell to Earth. That thought experiment stops being purely hypothetical once you recognize that the processes connecting it are confirmed at each step. The rocks that seeded Earth's chemistry came from a molecular cloud. The molecular cloud in another galaxy shows the same chemistry. The step between them is 4.5 billion years of solar system formation. The step between that cloud and a planet like Earth, somewhere in that galaxy, is whatever time it takes for a star to form, a disk to condense, and a rocky world to find its place in a habitable zone. That step may already be in progress. Water is the solvent of life as we know it. The question is whether life as we know it is the only kind the universe produces. On Earth, liquid water is the medium in which almost all biological chemistry takes place. Water dissolves organic molecules, allowing them to move freely and encounter each other. It participates directly in reactions, donating and accepting hydrogen atoms, stabilizing complex molecular structures, and enabling the folding of proteins. The properties of water, its polarity, its ability to form hydrogen bonds, its liquid range between 32 and 212 degrees Fahrenheit at normal pressure, make it a nearly ideal biological solvent. The prebiotic chemistry that Webb detected in frozen form inside the large Magellanic Cloud's molecular cloud will, under the right conditions, eventually be delivered to a planet. If that planet has liquid water, the chemistry proceeds along pathways that are well studied. The molecules dissolve, react, and under the right geological conditions, begin moving toward the kind of self-replicating chemistry that defines life on Earth. But scientists studying astrobiology have increasingly argued that liquid water is not the only possible biological solvent. Several other liquids have the right properties to support complex chemistry, and planets with those liquids in their liquid range may be far more common than planets with liquid water in the right zone around the right kind of star. Ammonia is the most discussed alternative. Liquid ammonia has a temperature range that extends far below water's freezing point, meaning it stays liquid on much colder planets. It dissolves organic molecules similarly to water. It participates in hydrogen bonding chemistry. On a planet orbiting a dim red star at the right distance, liquid ammonia could be a stable biological solvent for billions of years. Ammonia itself was detected by Webb in the ice mantles of the large Magellanic Cloud's molecular cloud, meaning any planet forming in that system receives ammonia as part of its chemical delivery. Formamide, a compound of carbon, nitrogen, hydrogen, and oxygen, has been proposed as a solvent for prebiotic chemistry in environments too hot for water or ammonia. Formamide stays liquid at temperatures up to 390 degrees Fahrenheit, covering a range of planetary environments where water would have boiled off. Laboratory experiments using formamide as the solvent for prebiotic chemistry have produced nuclear bases, the chemical letters of Dina and Rna, efficiently and reliably. Formamide chemistry is downstream from the methanol chemistry that Webb detected in ice mantles. Liquid methane, present in lakes on Saturn's moon Titan, has been proposed as a solvent for a completely different kind of chemistry, one that would use hydrogen cyanide as a building block instead of carbon dioxide, and that would produce cell membranes from acetylene rather than fatty acids. This kind of life would be unrecognizable by Earth standards, but the thermodynamic logic that allows it to exist is sound. The relevance to Webb's detection is direct. The molecules found frozen in the large Magellanic Cloud include precursors to all of these alternative solvents, not just water. Ammonia is present. The carbon and nitrogen chemistry that produces formamide is present. The simple hydrocarbons that could seed methane-based chemistry are present. This means the frozen molecular toolkit Webb found is not specific to water-based life. It is a broader chemical package that could seed multiple different types of chemistry on multiple different types of planets. The universe may be running more than one kind of life experiment simultaneously, and the starting chemistry for all of them appears to come from the same frozen source. What those experiments look like on a planet that has had billions of years to run, somewhere in the large Magellanic Cloud, is a question with no current answer and enormous stakes. The cloud collapses, a star ignites, a disk forms around it, and somewhere in that disk, at just the right distance, a rocky world begins to assemble. Everything that follows from there is a process that Earth went through 4.5 billion years ago, except in the large Magellanic Cloud, it is happening now. Or it happened recently. Or it will happen in the next few million years, which in galactic timescales is essentially now. When a rocky planet forms in the habitable zone around a young star, the first few 100 million years of its existence are defined by bombardment. Leftover debris from the disk, comets and asteroids that did not get incorporated into planets, fall inward and strike the planet's surface constantly. Each impact delivers heat, energy, and chemistry. The craters left behind on the Moon are the visible record of how intense this bombardment was in our solar system's early history. For a planet forming in a system that originated from a molecule-rich molecular cloud, that bombardment carries a specific chemical cargo. Comets formed in the cold outer disk carry ice mantle chemistry inherited from the parent cloud. Each impact releases frozen molecules onto the planet's surface. Water arrives in enormous quantities, eventually filling oceans. Organic molecules arrive mixed with that water, dissolving into the early ocean and concentrating at mineral surfaces, tidal pools, and volcanic vent systems. The geological conditions on the young planet interact with the arriving chemistry. Hydrothermal vents on the ocean floor provide heat, minerals, and concentrated chemical environments where reactions can proceed rapidly. Shallow pools on volcanic islands dry out and reconcentrate dissolved organics, driving polymerization reactions. Lightning in the early atmosphere adds energy to gas phase chemistry that complements the surface reactions. Earth's early geological record shows that microbial life existed by roughly 3.5 billion years ago, roughly 1 billion years after Earth formed. Some evidence points to biochemical activity even earlier, around 3.8 billion years ago, meaning life appeared on Earth within a few 100 million years of the planet reaching stable conditions. In geological terms, life appeared almost immediately. Scientists interpret that speed as evidence that the chemical jump from simple organic molecules to self-replicating chemistry is not the slow, improbable step it was once assumed to be. Given the right molecular starting conditions, the right geological environment, and enough time measured in tens of millions rather than billions of years. The transition happens if the same molecular starting conditions exist in the large Magellanic Cloud, because Webb confirmed the same frozen chemistry is there, then any rocky planet forming in a habitable zone in that galaxy begins its life with the same chemical advantages Earth had. The bombardment delivers the same package. The geological systems process it. The chemistry runs toward its outcomes. Whether those outcomes include life depends on factors scientists cannot yet observe from 160,000 light-years away. The planet's water content, the pH and mineral composition of its early ocean, the level of ultraviolet radiation reaching its surface. All of these shape whether the chemistry crosses the threshold into biology, but the chemistry getting to the threshold, rather than starting from scratch, appears to be guaranteed by the molecular cloud it was born from. The universe is not waiting for chemistry to get lucky. It is preloading the system. 30 years ago, finding a single amino acid in a meteorite was a headline result. Today, scientists find hundreds of distinct organic compounds in a single meteorite, match them to molecular cloud chemistry, confirm the same chemistry in star-forming regions across the galaxy, and now, with Webb's detection, confirm it in another galaxy entirely. The picture has shifted from amino acids being exotic space discoveries to amino acids being expected products of standard interstellar chemistry. The scientific consensus on prebiotic chemistry has moved significantly in the past 2 decades. In the 1990s, the dominant view held that the organic molecules needed for life were largely produced on Earth's surface through local chemistry, with space delivery playing a minor supplementary role. Meteorites and comets were interesting, but not considered primary contributors to the origin of life. By the 2010s, that view had reversed substantially. Isotopy analysis of organic molecules in meteorites confirmed that large fractions of Earth's organic inventory had interstellar origins. Detection of complex organic molecules in protostellar hot cores throughout the Milky Way showed that the molecular toolkit for life was being produced routinely across the galaxy. The comet delivery chain from molecular cloud to young planet became the mainstream model rather than the fringe one. Webb's detection in the large Magellanic Cloud pushes the consensus one step further. The chemistry operates in at least 2 different galaxies, under different conditions, producing the same molecular toolkit. The universality argument, once theoretical, now has direct observational support. The phrase scientists use increasingly in published papers and conference discussions is cosmochemical inevitability. The idea is that the production of prebiotic organic molecules is not an unlikely outcome of interstellar chemistry. It is an automatic one. Given a molecular cloud with any reasonable abundance of carbon, hydrogen, oxygen, and nitrogen, cold temperatures, dust grains, and time measured in millions of years, the production of complex organic molecules is essentially guaranteed. The numbers behind this consensus are striking. Every star-forming molecular cloud in the Milky Way studied in detail has shown organic molecular chemistry. Every comet measured with sufficient sensitivity has shown organic molecules. Every carbonaceous meteorite analyzed has shown thousands of organic compounds. The consistency across all of these different objects and environments is the statistical foundation of the inevitability argument. Adding an external galaxy to the sample, a galaxy with lower metallicity and different formation history, and finding the same chemistry strengthens the inevitability argument in a way that no additional Milky Way sample could. 2 independent data points are fundamentally more powerful than 2 samples from the same population. The industrial scale metaphor is accurate in a specific sense. Factories produce goods through repeatable, efficient processes that do not require special conditions or lucky accidents to operate. The molecular cloud ice chemistry operates the same way. Cold temperature, dust, radiation, time, the inputs. Amino acid precursors, sugars, nuclear-based precursors, sulfur chemistry, the outputs. Repeat across trillions of clouds in 2 trillion galaxies over 13 billion years. The volume of prebiotic chemistry the universe has produced by now is beyond any number that carries intuitive meaning. What fraction of it has crossed the threshold from chemistry to biology remains unknown, but the factory is running, everywhere, all the time, and it has been running since the universe was young enough that none of the stars producing the carbon to feed it had yet died. Probability is a number. Webb just changed it. Before this detection, scientists calculating the likelihood of life existing elsewhere in the universe had to work with an estimate for one of the key input variables, the fraction of planetary systems that receive a meaningful delivery of prebiotic organic chemistry. That fraction was based entirely on evidence from the Milky Way. The Milky Way is one galaxy, and however well studied it is, using one galaxy to estimate a universal fraction introduces enormous uncertainty. The detection in the Large Magellanic Cloud reduces that uncertainty in one specific direction. It removes the possibility that the Milky Way's prebiotic chemistry is a local accident driven by its specific formation history, metallicity, or stellar population. The chemistry appearing in a different galaxy with different properties is the first direct evidence that the prebiotic delivery fraction is genuinely high across different galactic environments. In the Drake equation, the framework scientists use to estimate how many technological civilizations might exist in our galaxy. One of the variables is the fraction of planets where life actually develops. This variable has historically been the most uncertain, ranging from nearly 0 to nearly 1, depending on which scientist you asked. Webb's detection does not directly constrain life's development fraction, but it constrains the prior condition, the availability of chemical starting materials. If prebiotic chemistry is universally available, then the question of life's frequency becomes almost entirely a question of biochemistry and geology. Does a planet with the right chemistry, the right water, the right temperature range, the right geological activity always eventually produce life? Sometimes? Rarely? The answer to that question drives everything. Scientists split roughly into two camps here. The optimist camp argues that life's chemistry is so strongly pushed toward its outcomes by thermodynamics, meaning the laws of energy and entropy that govern all chemical reactions, that any planet with the right starting conditions will eventually produce self-replicating chemistry. On this view, life is the thermodynamically favored outcome of complex chemistry in wet, warm, energy-rich environments. The cautious camp argues that the specific steps between prebiotic chemistry and a self-replicating molecule remain genuinely difficult to explain. The jump from chemistry to biology may require a very specific sequence of unlikely events even given the right starting materials. On this view, life is possible but not automatic. Webb's detection does not resolve this debate, and scientists are honest about that. But it sharpens the debate by removing the chemical availability question from contention. The molecules are there, everywhere. The debate is now squarely about what happens next. That sharpened debate is itself a scientific advance. Research can now focus on the biochemical and geological steps that are genuinely uncertain rather than spending effort confirming that the molecular starting materials exist. If the optimist camp is correct, the universe is populated with life on a scale that humans have no cognitive framework to appreciate. If the cautious camp is correct, life may still be rare, but it is rare because of biochemical bottlenecks rather than chemical scarcity. Either way, the universe has been doing its part. The chemistry is preloaded. Frozen, waiting, what decides whether it wakes up is the question that every major space observatory launched in the next 50 years will be designed, in part, to answer. Webb opened a door. What comes through it depends on the instruments scientists are building right now. The next generation of large space and ground-based telescopes is being designed with specific goals that build directly on Webb's capabilities. Where Webb detected simple and moderately complex organic molecules in ice mantles, the next generation aims to detect molecules that are 1 or 2 steps further along the chemical chain toward biology. The most targeted next step is the detection of glycine in its frozen form. Glycine is the simplest amino acid and has been found in comets and in the gas phase near hot cores in the Milky Way. Finding it in its frozen form inside an ice mantle in a molecular cloud has not been accomplished. Frozen glycine would confirm that the full amino acid production pathway operates in cold cloud environments, not just in the warmer regions, near newborn stars. Webb has the sensitivity to potentially detect frozen glycine, but requires a specifically designed observation program targeting a very bright background source. That program is in the proposal stage. A second priority is the detection of ribose, the sugar molecule that forms the backbone of RNA. Ribose has been found in meteorites, but its interstellar production has not been confirmed. Models predict that it forms through reactions between formaldehyde molecules in ice mantles, a reaction chain that starts from the same methanol chemistry Webb confirmed in the Large Magellanic Cloud. Detecting ribose in a molecular cloud would close one of the remaining gaps in the from cloud to biology chain. The extremely large telescope, currently under construction in Chile and scheduled for first light in the late 2020s, will be the largest ground-based optical and infrared telescope ever built. Its mirror stretches 128 feet across, roughly 6 times wider than Webb. Its resolution will exceed Webb's for certain kinds of observations, and its spectrographs will push the detection limit for complex organic molecules further than any current facility. The Habitable Worlds Observatory, a planned NASA flagship mission for the 2030s, is designed primarily to directly image Earth-sized planets around nearby stars and analyze their atmospheres for biosignatures. One of its secondary science goals involves characterizing the organic molecular environment around young planetary systems, connecting the interstellar prebiotic chemistry to the atmospheres and surface chemistry of the planets that form from it. What scientists are ultimately looking for is the closing of the observational chain. Webb confirmed the first link, frozen prebiotic chemistry in molecular clouds outside our galaxy. Future telescopes will try to confirm the delivery link by measuring organic molecules in the atmospheres or surface environments of young planets in star-forming regions, and eventually the biology link by detecting biosignatures in the atmospheres of mature planets in habitable zones. Each link confirmed tightens the argument. Each confirmed link also raises the stakes for the final question: are the atmospheres of habitable planets already carrying the signatures of living chemistry? Right now, in galaxies we can observe. The telescopes being built now may answer that question within the lifetimes of most people who will hear this. Webb's frozen molecules in the Large Magellanic Cloud are, in this light, the opening signal of a search that ends either with the confirmation that life is everywhere, or with a discovery about what prevents it from crossing the final threshold. Both outcomes change everything. The molecules were there before the stars that could warm them, before any planet formed in the Large Magellanic Cloud, before any ocean pooled, before any chemistry came close to crossing the threshold into biology. The frozen molecular toolkit was already there, inside the cloud, waiting inside ice mantles on dust grains drifting in the dark. This is the detail that carries the most philosophical weight. The universe does not wait for planets to exist before manufacturing the chemistry of life. It builds the inventory first, in the molecular clouds that will eventually collapse into the stars and planets of the next generation. The chemistry arrives at the planet before the planet has even finished forming. That sequence inverts the mental model most people carry about where life's chemistry comes from. The intuitive picture is that a planet forms, develops geology, develops an atmosphere, produces complex chemistry locally, and eventually, after an enormous amount of work, stumbles toward the molecules needed for life. The actual picture, supported by every line of evidence from meteorites, comets, hot cores, ice mantle chemistry, and now Webb's detection in another galaxy, is that the planet receives most of its prebiotic chemistry as a gift from the molecular cloud it formed from, and the geological work is to process and activate a package that already arrived. This picture has philosophical implications that scientists often acknowledge carefully because science does not make claims about meaning. But several scientists involved in this field have noted publicly that the consistent universality of prebiotic chemistry, its appearance in every molecular cloud studied, in every galaxy examined, under conditions ranging from rich Milky Way clouds to the lower metallicity environment of the large Magellanic Cloud, suggests that the production of life's ingredients is a structural feature of the universe. A structural feature is something built into the rules rather than something that happens accidentally. The laws of physics and chemistry that govern how atoms bond, how ice mantles form on dust grains, how radiation drives molecular complexity, these laws are the same everywhere in the observable universe. They were the same seconds after the Big Bang. They will be the same long after our sun exhausts its fuel. And they consistently produce the same prebiotic molecular toolkit wherever the right conditions arise. The philosopher's version of this observation is that the universe appears to be organized at a physical level to produce the chemistry that enables life. That statement does not require any supernatural interpretation. It is a direct description of what the evidence shows. The chemistry is not an accident in the sense that it does not depend on rare or unusual conditions. It is a consequence of ordinary physics operating in ordinary environments. What that means for questions of purpose, significance, or humanity's place in the cosmos is a conversation that science opens but does not close. Each person who hears this evidence carries it into their own understanding of what the universe is and what they are doing in it. What the science says is this: the frozen chemistry sitting inside a molecular cloud 160,000 light-years away in another galaxy contains the same molecules as the ones inside every cell in your body. They formed the same way. They followed the same chain from dust grain to comet to planet to life, or the beginning of that chain. The universe ran the same process in a different galaxy and arrived at the same molecular result. Whatever that means, it is real, it is measured, it is confirmed. And the part of the story that has not yet been written is what that chemistry becomes on a planet somewhere in the large Magellanic Cloud, in the billions of years that still lie ahead. The telescope is already pointing somewhere new. Webb's schedule is filled years in advance, a reflection of how many scientists are competing for time on an instrument that can do things no other observatory has ever done. The detection in the large Magellanic Cloud triggered an immediate wave of follow-up proposals, each building on what that discovery confirmed and trying to push one step further along the chain. The first category of follow-up involves more clouds in the same galaxy. The large Magellanic Cloud contains dozens of dense molecular clouds in different stages of evolution, from cold and chemically inactive to actively being irradiated by nearby young stars. Mapping the ice mantle chemistry across these clouds would show how chemical complexity changes as a cloud ages and heats up, providing the first developmental atlas of prebiotic chemistry outside the Milky Way. The second category targets other local group galaxies. The small Magellanic Cloud, the Milky Way's other nearby companion galaxy, has even lower metallicity than the large Magellanic Cloud, if ice mantle chemistry operates there at comparable complexity. The metallicity threshold for prebiotic chemistry production drops further, expanding the range of galactic environments where life's ingredients can form. Andromeda, the nearest large spiral galaxy at 2.5 million light-years, is at the edge of what Webb can reach for this kind of absorption spectroscopy, but a bright enough background source might make it possible. The third category involves the molecular clouds within our own galaxy that are most similar to the large Magellanic Cloud's chemistry environment. Several outer Milky Way clouds have lower metallicity than typical inner galaxy clouds, making them better analogues for comparison. Detailed ice mantle inventories from these clouds, analyzed with the same pipeline used for the large Magellanic Cloud detection, would test whether the universality argument holds even within metallicity variations inside a single galaxy. Webb also has dedicated programs targeting protostellar systems, young stars still surrounded by their birth cloud material, to measure how the ice mantle chemistry changes as it transitions from the cold cloud phase to the warm disk phase where planets form. Catching complex organic molecules at that transition point would close the first gap in the cloud to planet delivery chain. Scientists working in this field have identified a specific list of detections they hope to achieve before the end of the current decade. Frozen glycine, an amino acid in a molecular cloud, phosphorus-bearing molecules in ice mantles, confirmation of ice mantle chemistry in at least one galaxy beyond the local group, direct measurement of organic molecule delivery into a protoplanetary disk. Each of these detections would close a link in the chain. Taken together, they would produce an evidence base for the molecular seeding of planets that is so complete and so consistent that the argument for universal prebiotic chemistry delivery would shift from strong to definitive. The decade is not over. Webb is operational. The archive is full of unanalyzed data, and the molecular clouds of the universe have been keeping their frozen records for millions of years, waiting for a telescope sensitive enough to read them. One telescope already has. What it reads next may be the most significant scientific result of the century. The chemistry is there, frozen in the dark, 160,000 light-years away, waiting